Hello and good afternoon, everybody. Welcome to PCM's second webinar on PCP myths and truths. Firstly, thank you very much for taking the time out of your schedules to join us. Myself and Paul, Benjamin as well, who today hopefully will be having a useful session to better understand common myths and truths that many operators face all around the world. My name is Reza Bakhtiari, and I'm the Oil and Gas Manager for the Asia Pacific region based in Brisbane, Australia. We have also Benjamin Robert coming with us from Chantosay in France, as well as Paul, who's the presenter for today, and he's also based in Chantosay. Paul joined PCM in 2019 as our ALS product champion, and before that, he was with SEVERITY for 23 years as a senior engineering advisor. I think some of you have already had the benefit of Paul's extensive experience in the past, and fingers crossed he can be useful for you again today. So just to recap, this is a one-way audio system, so we can't hear any questions from you. But on the right-hand side of the page, you should see some questions and answer boxes. So if you have any questions during the presentation, please just type your questions in there. We'll review them and then publish them, so we can hopefully have an answer to all your questions by the end of this webinar. So I won't keep you any longer and hope you enjoy the webinar. And I will now send you over to Paul.
Hi, everyone. So depending on where you are, good morning, good afternoon, welcome. So we'll talk again today about some more myths and truths. For those of you who saw the last session we did, it's going to be short on each topic, one slide for each. So it's just a quick summary. I'm always happy to discuss things in more detail offline. So let's just switch straight into the presentation here. Just wanted you to see my face before we get started. I'll turn the face back on when we get to the questions and answers later. But so again, as Reza said, we'll do questions and answers at the end. We'll talk more about that in a second here. So part 2, PCP myths and truths. So here's our list for today. The topics we came up with, this was a group meeting at the PCM. These aren't all my ideas. This was a collective discussion between the last time and this time to come up with a list of these topics. So I hope I can give a good summary on each of these for you. As we go forward through this, some of the topics that I'm going to show as a myth are in fact often true. The myth is that they're always true. Sometimes people think in black and white, and unfortunately the world isn't black and white. There's always a lot of gray in there. So some of these statements that you see on this page here might be often true, maybe even usually true, but not always true. And probably there's a couple that just aren't true, but we'll get to those. All right, so as we said, yeah, questions we'll save for the end. And go ahead and find your Q&A section if you want to start asking questions, and you can start typing your questions at any time, and we'll get to those at the end. All right, so let's get right into it here. Our first topic: a PCP cannot run at 90 degrees hole angle. It's referring to here. That's a myth. There's nothing at all that says a PCP can't run at a very high angle. In fact, some people will take the PCPs beyond 90 degrees and go up to 92, 93 degrees in some cases. It's really not the hole angle that matters. What matters is the dogleg severity in the well bore and the dogleg severity where the pump is landed. Those are two different things, of course. When the DLS is high, you're going to have problems with the rod string. That's the real issue here. Holes in tubing because of rod tubing wear, or broken rods due to rod fatigue. These are the problems that you get with highly deviated wells. You need to address those problems with proper rod string design. People often ask, what's the maximum DLS for a PCP? And again, except where the PCP's landed, it's not the pump that matters, but the rods. I've seen wells with 12 or maybe even 15 degrees per 30 meters or degrees per 100 feet. If you're that high a curvature, rod string design is critical. It's going to be very difficult to get a good long run life out of your rods. If you get the DLS down below 5 or 6, it gets a lot easier, but in some wells you can still have some significant problems with your rods. So it's again, rod string design should always be considered carefully when you're in a deviated well. The PCP can run through any dogleg that you're gonna be able to come up with a reasonable rod string design. So it's not the running the pump that's the problem. It is important, however, to have a straight section or a tangent section where you land the pump. You don't want the pump to be curved when it's actually running. If it is, you're gonna end up with broken rotors. So you want to have a straight section there. The rule of thumb for that is 3 degrees or less per 30 meters of dogleg. It's a good rule of thumb. It's not perfect, of course, like most rules of thumb. It's a good guideline, but has exceptions. If you have a very long pump, or if you have very tight clearance between the pump and the casing, then you'll need that tangent section to be straighter than that. But in most cases, that's fine. Space out is a problem when you get into deviated wells, and the higher the hole angle, the more difficult it can be, simply because gravity isn't pulling the rotor down into the pump for you. So you can't always tell when the rotor's in the stator. So it takes a rig crew with a bit more experience to be competent at doing space out in a very high angle well or wells with very high dogleg in them. There are cases where sometimes they'll use a little bit of pressure from surface to push the rotor into the stator too. So yeah, so it's just PCP can certainly run beyond 90 degrees, but your rod string design is critical and space out can be difficult. A good PCP should have test bench efficiency of 60 to 80%. Now I'm going to say myth on this. It's not the test bench efficiency that matters, it's the efficiency downhole. But before I get to that, I want to state one thing that's, I think, pretty important. When we talk about test bench efficiency, pick a number, 60%, that doesn't mean anything by itself. You always have to state your test bench efficiency at a speed, pressure, and temperature, especially speed and pressure. Because I can get, if I can control the speed or pressure, I can get 60% easily with any pump. It doesn't matter what pump it is. I can find conditions that'll be 60%. So it doesn't mean anything by itself. So typically you want to say I want 60% or whatever your number is at rated pressure at 300 RPM and at whatever temperature, say 50 degrees Celsius or 20 degrees Celsius. You pick your number depending on what your reservoir is. So it's important to make sure we have that distinction. But getting back to the whole point of the slide, the bench test is intended to give you a relative indication of the tightness of a pump. It's not going to tell you what happens downhole. There's too many things that are different downhole than there is at surface. There's a list on the slide here, but there's just so many things that are different, and we know that you have to, in many cases, you're going to choose a bench test that's very different from what you see, a bench test efficiency that's very different from what you want to have downhole. And I know of cases where people's target is 0% on the bench to get good performance downhole because the elastomer swells up or it's higher viscosity fluid or something like that. I've even seen cases where instead of saying we want 0% of rated pressure, they say we want 0% at 70% of rated pressure or something like that. It's even looser than 0 at rated. So please don't expect a bench test to show you exactly what's going to happen downhole, because it won't. Some of the differences here: fluid viscosity. I know a lot of people listening today are in Australia and you're pumping water, so that may be not a huge effect in Australia. But in other parts of the world where you're pumping oil, viscosity has a very large effect on efficiency. But the rest of these can occur everywhere. Elastomer swelling, that's the big one. And this is what you'll never be able to simulate on a bench test because the swelling is dependent on the reservoir temperature, pressure, and most importantly, the fluids. And we might be able to get the temperature right, but almost all bench tests can't get the pressure right because they're done with intake at atmospheric pressure. And you'll never get the fluids right. We're not pumping produced fluids through our test benches. We're pumping water, maybe with a little bit of a well-controlled oil added to it. So it's not the same as what you're pumping downhole. You're not going to see the same swell. And secondly, swell takes days to weeks to sometimes even months to fully happen. So in a bench test lasting, minutes to maybe an hour or two, usually the pump's just not going to swell up that much. So that's not going to be, you're never going to get that representation on a bench test. Next is the temperature profile inside the pump. This also, temperature leads to thermal expansion. It looks just like swell. The temperature profile in the pump is going to be very different on the bench test than it is downhole, largely because the bench test is out in air. It's on a bench. You're pumping water through. You can control the temperature of the water, but the outside is exposed to whatever the room temperature is. So the longer you run that pump, if you're pumping 50-degree water through it, for example, 50 degrees Celsius, it's going to be nice and warm on the inside, but the profile inside the pump is not going to be the same as if it was immersed in a reservoir at 50 degrees Celsius, where the outside is also at that temperature. So you're not getting the same temperature profile, which means you're not getting the same thermal expansion. And secondly, on that point, it takes a long time for temperature to stabilize. Even on a test bench in air, we've done tests at PCM where we've run a pump for up to an hour or even longer in some cases, and watched the temperature profile, watched the stator temperature. So we measured the outside temperature of the stator and measured the efficiency over time, and we saw that it just continued to increase for 40 minutes to an hour in some cases. And this is it's big because if you look at the ISO 15136-1, it describes in there how to do a bench test per the standard, and there's a temperature control criteria in that standard. It says, I forget what it is, it's a certain number of degrees Celsius in a certain period of time. And we showed with our testing that even following that criteria is not adequate. It doesn't show you what the true performance of that pump is because you can let the temperature warm up even further, and even though it's changing less than what the number in the standard is, it's still causing a significant effect on the results. So temperature profile is huge, and we're never going to match that on a bench test. Well, I shouldn't say never, but to do it would be very, very expensive, and I don't think anyone wants to pay for that. So then there's some well conditions like gas. If you've got gas going through your pump, you're measuring efficiency based on liquid rated surface. Yeah, if you've got gas in the pump, the efficiency is going to be lower, and that's just normal. And even in your coal gas wells where the pump's below the perforations and you think the gas is going up, even just a couple of % of gas going down to the pump, just being carried by the fluid down to the pump, can affect that efficiency noticeably in some cases. So you might think your gas is all going up the casing, but if it's not, then it will affect your efficiency. If you pump the well off, of course, your efficiency is going to go down. There's nothing a bench test can do to predict that. Any kind of inflow restrictions, typically we talk about heavy oil here, but it could also be plugging of your intake or anything like that. If the fluid can't get to the pump, obviously your efficiency is going to go down, and no bench test can predict that either. So there's lots of things that can make a bench test different from what's going to happen in reality. So your goal is to reach whatever your efficiency you want in your wells. So 60 to 80% might be a good range, a good target to aim for in your well. The question is what bench test efficiency will get you there, and that's the black art of this business, and takes some experience. And certainly the pump suppliers like PCM and other companies can help you with that as well. All right, next myth here. Every PCP system needs a torque anchor installed. And this is one of those ones where it's often a myth, or it's not always true. The myth is that it's always true. It's not necessary in all cases. It's certainly recommended. Most pump companies will recommend that you run a torque anchor just for safety. But there's lots of times where companies don't, for whatever reason. They might have their own reasons for doing it. Some reasons include instrumentation. If you're running an instrumentation line, it can be awkward to have a torque anchor, and some companies have had experience that the torque anchors slip a little bit once in a while. Not enough to cause a problem with your tubing string, but if you have an instrumentation line, it could slip enough to break that line. If you've got a complicated completion, such as multiple tubing strings or various other types of completions, then it might not be possible to run a torque anchor. Even in some simple wells, I know there's some wells, I think even in Australia, they're shallow, maybe 200 meters deep, but they're pumping 5,000 barrels a day with a big pump, and they're not running torque anchors. So it's possible to do this. So how can you make up? How can you reduce the probability of having your tubing unscrewing without a torque anchor? There's a few different things you can do. If your torque is very low, maybe you don't need to do anything. If your torque's a bit higher, then you want to look at it. And if you look at the makeup torque of tubing, it's substantially higher for any, I've got some numbers there for 3.5-inch tubing. Obviously, if you go down to 2 7/8 or 2 3/8, the numbers get smaller. But you're probably running smaller pumps with lower torques in those wells, so it doesn't really matter. Now those makeup torques are a lot higher than the torque we're going to put on a rod string. A typical 1-inch rod is good for about 1,000 foot-pounds, so it's less than half, sometimes less than a third of what we see in this table here. But we still know that tubing can come unscrewed. It does happen. The EUE tubing breaks out, or can break out at a lower torque than the makeup torque, and especially when it's under vibration. And we know PCPs vibrate, so that can happen. Even though you've made the tubing up to over 2,000 foot-pounds, it can still unscrew during operation. The more premium type connections, where there's a shoulder connection in them, the shoulder connections typically take higher torques to break out, higher than makeup, so you can get better performance there in terms of not having your tubing unscrew. So just for some comparison here, you can see in the table there, so a standard 3.5-inch J55 EUE tubing, the optimum makeup torque for that is 2280 foot-pounds with a maximum of 2850. If you just go up to a higher grade of tubing, L80, it goes up to by about 1,000 foot-pounds. So you get to higher torque already. If you go to a premium connection, now I haven't listed the brand name on here. I did go onto a catalog and look for a common premium tubing and checked it out. The odd thing was for that particular brand, if I went to J55, the makeup torque was actually less. So I'm not sure why, but for L80, you can see it's a 3,800 foot-pounds. It was for optimum makeup, so pretty high torque there. If you don't want to use L80 premium tubing, what can you do with your J55 EUE? There's a couple of different companies in Canada that sell some products that you can just work with standard J55 API tubing to improve their torque capacity. One of them is a torque ring. It just fits inside the standard EUE coupling and basically acts as a shoulder between the two ends of the pipe. And you can see there, they haven't published an optimum makeup torque, they published their maximum of 3,800 foot-pounds. So you can see it's comparable to some of those other higher end tubings. There's also a special coupling that's available from several manufacturers in Canada. It's patented by one company, but there's 2 or 3 that actually make it. And that's, again, it's got an optimum torque of 3,500 foot-pounds. So it's, again, pretty similar to those torque rings. So again, those things are all available. If you really don't want to run a torque anchor for some reason, these are things you can do to try to avoid that need. Choking the tubing is a way to reduce free gas at the pump intake. I've heard this one a couple of times in the field, but I'm not the one who put this one on the list, so obviously other people have heard this one as well. And I'm going with myth on this, and I know there's probably going to be people out there who argue with me, but I've never heard a good explanation on this one, so I'll give you my explanation here. Choking the tubing affects only what's in the tubing from between the pump discharge and surface. The PCP is a positive displacement pump. It's not changing the pressure in the tubing, is not going to do anything to what's happening at the pump intake. It is going to make the pump work harder. You're going to have higher torque in there because you're working against higher pressure. But also, when you have higher pressure, you're getting less of a gas lift effect from the gas. Once the gas is in the tubing, it actually helps you. It's only when it's going through the pump that it's bad. Having the higher pressure there is bad in a couple of ways. The one thing it might help you with, I don't have this on the slide, but if you have slugging in your tubing, and if that's causing you problems with your surface facilities for some reason, then it's possible, depending on the situation, that choking the tubing could reduce that slugging. But it's not changing the amount of gas going through the pump. So if you're trying to reduce free gas at the pump intake, it's not going to help. If you do want to reduce the free gas at the pump intake without changing anything downhole, anything in your completion, the only thing that's going to work is to increase pressure at the intake. And to do that, you need to have a lower production rate. And nobody wants a lower production rate. So it's difficult. In theory, yeah, the note on the slide here, if choking the tubing increases slip in the pump, you will decrease the production rate, but it would be better for the pump and cheaper overall to just reduce the pump speed in that case. What about choking the casing? That increases the pressure in the casing. If you've got gas coming up the casing, you can choke down the valve there and increase the pressure in the casing. That won't actually change the pressure at the pump if you're not changing the flow rate, though. It'll push the fluid level down. You're just exchanging casing pressure for fluid level. It's not going to affect the pressure at the pump. It's not going to affect the pump intake pressure. So not going to help that way. Obviously, changing your completion is the way to solve free gas to the pump intake. The deeper you can get the pump, the better. There's some gas separators on the market that may or may not work in some cases, so those are options to look at as well. The deeper your pump, the higher the pressure. So even if you can't get the pump down below the perforations, which is the best thing to do, still the deeper the pump, the higher the pressure, and any gas there will have a lower volume. So those are the solutions. Well, not necessarily always solutions, but things you can do to improve or to reduce the free gas at the pump intake. Choking at the tubing is probably not going to help. When the rotor enters the stator during installation, the rig crew will see the rod string rotate. This is usually true. The myth here is that it's always true, especially when you get into deviated wells. And I mentioned earlier that it can be difficult to do space out in deviated wells. Yes, there is a tendency for rods to rotate when the rotor enters the stator. The rig crew will often see it. If it's a vertical well, you'll probably see it every time. But when you get into deviated wells, if there's any friction along the rod string between the rod and the tubing, if that friction is enough to overcome the friction torque of the pump, then the rods may not rotate. So I have a little animation here. This is just a little 3D printed model of a PCP that I borrowed from one of my colleagues. And I'm just sliding that rotor in and out here without rotating it. So if you have a little pump model, I know a lot of people have these on their desks because some of the pump companies give them away at shows. Try it. Try and slide the rotor in and out. If it's a tight pump, you might have some difficulty doing it. The tighter the pump, the harder it is to do. It's certainly easier to make it go in by rotating it, but it doesn't have to. This is not like a bolt going into a nut. It doesn't have to turn to go through. It will go straight in without turning. If you stop it from turning, it will go in. So the whole point of this is space out. When the rig crew is installing the rod string, they need to know when that rotor enters the pump and when it hits the tag bar. And one thing they do is they watch for rotation, because that tells them the rotor is going into the stator. But when you're in a deviated well, you might not see it. So the rig crews need to know that, especially if they've never done a deviated well before. It can be very difficult to do space out properly there, and the rotation is one thing that, while it usually helps you, it's not guaranteed to be there when you get into these deviated wells. Okay. Here's one. When there's a high dogleg severity, we talked about rod string design earlier. The use of pony rods or rod guides can help improve system run life. Well, look at this one. It's true. Sometimes the people have the idea here, so there's a bit of a myth, I suppose, that short rods are less flexible than long rods and therefore under higher stress and will have higher contact loads. And first off, while a short rod is less flexible than a long rod, when you have the same length of rods, whether those are 10-foot pony rods or 25-foot rods, by the time I've got 100 feet of it, it actually doesn't change the flexibility very much at all. You've still got 100 feet of rod. Sure, there's a few little connections in the middle that are stiffer, but it's a few percent different. It's not going to affect the flexibility of a rod string very much. It's not the individual rods we're worried about here. It's the rod string. But then here's the real key point: is the flexibility doesn't actually matter. This I would need more than 2 minutes to explain this to you, so I'll leave it at that. But once you get into a well, when you have the rod string under tension, once the rod string's under tension, it's not the flexibility in the rods that matter anymore. It's how much tension is there. That's the tension and the curvature of the well. That's all you need to calculate the contact loads, which is what leads to wear. There's nothing else that goes into that calculation. So the idea of having pony rods or rod guides, basically having more contact points in the well, the more contact points there are, the more the load gets spread out. The total contact load will be the same. For a given amount of tension and curvature, the total contact load is the same. But when you spread it among more points, the contact load at each one is less. So then you get less wear at each of those points. So that's what works there. So the next one is rod fatigue. Calculations are very different for fatigue. And I could talk for probably an hour on fatigue if you wanted to hear me talk about it, but the biggest factor in the fatigue calculation is what's the curvature of the rod near the connections. The curvature does not evenly spread out through the rod string. It gets concentrated at the connections, and there's a bunch of factors that go into that. But one of the factors, one of the very important parts of that calculation is what's the distance between the contact points. So by having pony rods or rod guides, you're reducing the distance between those contact points, and it really has a huge effect on that concentration of curvature, and can really improve fatigue life. So, so yes, having shorter distances between your contact points, whether those are connections or rod guides, improves both wear and fatigue. Downsides, of course, higher cost. You've got more, if you're buying rod guides for your rods, then that's an extra cost, of course. If you're buying more connections, I'm sure 100 feet of pony rods cost more than 100 feet of standard rods, just because there's more connections in there. And also in rig time, if you're making up these pony rods, it takes a lot more time. So there certainly are other factors that we can talk about in here. It does mention there increased pressure loss in viscous oil. That's an interesting one as well. The more upsets you have in the well, whether those are guides or contacts, if you're pumping with viscous oil, that's going to increase your pressure loss. I did have a customer once many years ago who was using software to design his rod string, and he was trying, he had high contact loads. The software was predicting high contact loads, and so he added more rod guides, thinking that would reduce the contact loads, as I've just said. And for his case, it wasn't. He added more guides and it wasn't changing the contact force, and he thought something must be wrong with the software. So he asked me about it, and I looked at his case, and what was happening for him was that he had high viscosity fluid, and every time he added more guides, he ended up with a higher pressure loss, which put more load on the pump, which put more tension on the rods, which increased the contact loads, and it actually just balanced out. So it wasn't helping him to add more guides. But that's a very rare case. And certainly for those of you who are in pumping high water cut applications, the rod guides, that's not the downside. It's cost for you. That's the only downside. Now clearly rod guides, if they're molded onto the rod, which is the best kind of rod guide, I think, in my opinion, they're rotating with the rod and they're rubbing against the tubing, so you still can have some tubing wear on them. The spin through centralizers, several companies including PCM sell those to go. You can put those on pony rods, you can put them on standard rods, and they do a really good job of reducing wear. So if you're using those, especially with pony rods, then you've got a great rod string. If you're having full length rods, maybe you got your spin through centralizers on the connections, but you've got guides in the middle, you're still gonna have a little bit of wear there. So again, careful rod string design is essential. Make sure that you've got a high enough predicted life on your tubing to not have holes before you're going to be pulling the rods for other reasons, or pulling the tubing for other reasons. There's certainly lots of other rod string designs you can look at as well for reducing wear or fatigue or both that go beyond this. So this is not the only solution to designing a rod string. There's lots of other things you can do, but this was just one. Right, so that's it. One slide on each of those topics for about 25 minutes. That was pretty good timing, I think. So, the conclusion, Lots of beliefs of PCP. So this is the same conclusion slide I had in the last one. There's lots of beliefs about PCPs in the industry, and I'm sure in any other artificial lift they have their own sets of myths as well. A lot of them are based on fact, and in fact are often true, but not always true, and can be oversimplified. So we want to be careful in how we interpret these common beliefs or rules of thumb, etc. So we'll take questions now. If possible, restrict it to talk questions about today's, but we'll take any reasonable question. I'm certainly happy to talk as much as you like offline. If you want to debate some of these points with me, we can do that offline. Or send me an email, and we can arrange a discussion through Teams or some other means. Keep an eye on our LinkedIn page for announcements for future webinars. We don't have anything scheduled or planned right now. I'm not sure what the next one's going to be or when it's going to be. Hopefully it'll be about a month from now, but I don't know. And I don't know what it's going to be. So yeah, just keep an eye on our LinkedIn page, and we'll update you when we have a plan. So there's my email address, and our website are there. So at this point here, what do we have for questions? We have a few questions that are here. Oh yes, Benjamin's put my face back on the screen, so you get to see me as I'm reading questions and answering them. Okay. How big an impact does the pump swept angle, pump geometry have on its solids handling capability? There's an excellent question. There's the traditional theory, and then there's what's being proven. And those may not be the same. Traditional theory says that lower swept angle, shorter pitch, however you want to measure it, and there's a bunch of different measures that people have in the industry, but basically they're all a measure of pitch length or the aggressiveness of that spiral, really short, tight spiral. The general feeling has generally been that is a better for solids. So the more aggressive pitch, short pitch, low angle is better for solids. That's the general feeling in the industry. Data I've seen seems to support that. But in fact, nobody's done any that I've ever seen published. Nobody's ever done any actual testing on that with controlled laboratory studies with comparing what happens in different applications or with different pump geometries. So I can't prove it to you. I know that in Australia a few years ago, I met a guy who worked for one of the companies who was trying to argue that long pitch pumps were better because they had higher velocity inside them, and it's velocity that has to carry the solids in low viscosity fluids like water. So at that point, it's a question. Okay, we have hand waving arguments on either side, but I'll come back to what I've seen with in my previous life at a different company when I was able to see reliability data. Really seemed to suggest. It wasn't, it wasn't 100% conclusive, absolutely, no question about it type of data, but the data certainly was showing that the shorter pitch pumps did better for solids. So I'm gonna stay with that answer until someone proves me wrong. I'd love to see some actual test data on that. Next question. How about efficiency slippage with deviation angle? As far as I know, and if you have some data to show me wrong on this, I have never seen any indication that the slippage in a pump should change based on the deviation angle. We do bench tests horizontally. A lot of wells are vertical. We've never expected there to be a difference in performance when you move that pump from a horizontal test bench to a vertical well. Not noticeable anyway. Where it could change is when you start getting gas. If it's not slippage that's causing your change in efficiency, but it's gas coming in, you're going to get different separation in a deviated well than you would in a vertical well. So that can affect your efficiency, but for slippage, I just don't think so. What would happen if you place the pump at DLS more than 6 degrees? Would that affect the rotor? The short answer, I think, is probably yes. I think you're going to see broken rotors if you're running with the pump landed in a high dog leg. You can run the pump through that dogleg, it's not going to cause any problems at all, but to land it there and start rotating the rotor, that's when you start to get broken rotors. Now, again, I gave the rule of thumb was 3 degrees. There's always some fuzziness in a rule of thumb, and there's actually calculations you can do to figure out if your pump is going to be bent or not based on the dogleg severity, the length of the pump, and the clearance between the pump and the casing. So if you got very tight clearance, the worse it's going to be. If you got a 3-inch pump in 9 5/8 casing, you can get away with a lot more DLS. Same thing if your pump is really short. So it does depend on the length of the pump and the clearance. But in general, if the pump is going to be in a bent condition, it's going to you have a risk of having rotor breaks due to fatigue of the rotor. What geometric and elastomer considerations will help with solids handling in PCPs and other than swept rotor angle? Obviously, elastomers are going to have a difference, and I know there's different opinions in the world about which elastomers are better for solids, but each manufacturer has its own elastomers that it will recommend for solids, and I'm not going to try to compare one manufacturer to another. But within each manufacturer, they should have a good indication of which of their elastomers are better for solids. And yes, some of them are more abrasion resistant than others. So yes, you'll want to make sure you're picking the right elastomer for solids application that way. Other geometry considerations, like I said a few minutes ago, there are several different parameters people will use to calculate or to estimate the geometry effects. The bottom line is nobody's done testing to actually prove if any of these is better than the other, and they're all pretty highly correlated with each other. There are some exceptions in there if you get some pretty extreme D/E ratios of your pump, so pumps with very small eccentricity or pumps with very large eccentricity. It might screw up the correlation on these factors. But if you take swept rotor angle, for example, and you correlate it with, I know Weatherford has what they call the geometry index. If you plot those against each other, you get a pretty tight grouping. It's a curved line, but there's a line that the pumps all follow, and a pump that's high in one is high in the other. Again, with the exception of these very low or very high eccentricity pumps. So they're basically telling you the same thing one way or the other. So I don't have a strong opinion. I'm not going to swear to you that the swept angle is the one measure to use. No, there's lots of different measures of the aggressiveness of that pitch angle, but I think, again, nobody's proven it yet, but the general indication seems to be that the short pitch is better, and just find a way of measuring that, and swept angle is one way of doing it, geometry index is another way of doing it, and there's probably a few more out there. So I don't think that one's better than the other on that. But until someone proves me otherwise, I'm going to still say we want to go with a short pitch pump for solids. Someone's asking about clarification on the makeup tubing to maximum torque level. So for EUE tubing in particular, there are charts available in the industry that give a minimum, maximum, and optimum makeup torque. Those are published numbers, and it's generally not based on the tubing body, but the connection, the threads, because those are cut into the pipe. So the weak point is usually the threads. Although with EUE, it's external upset, so there's actually a little more strength there, so it may account for the pump body as well. Sorry, the pipe body. But those are published tables. Minimum, maximum, optimum. So depending what your rig crews are doing, I don't know if they're measuring it at all, or if they're calibrating their equipment to give that torque. But if you're not running a torque anchor and it's something you want to look at, you look at that minimum, optimum, maximum, and you want to be towards the maximum end of it. For whatever grade and size of tubing you've got, again, those are published values. If you're using a premium tubing, then you go to that tubing manufacturer. They're going to have a published value for what that torque is. So yes, it's if you're running without a torque anchor, I would recommend going to the maximum torque that tubing or connection is rated for. That's I hope that clears that up. Rotor stator interference for solid handling. Is a tighter fit better for solids handling or a looser fit? And I mentioned a few minutes ago with the different companies have different recommendations for the elastomer, and I think that correlates with this as well. People who recommend tighter fits tend to recommend looser or softer elastomers, and people who recommend looser fits go with the harder elastomers. So I personally don't have an opinion if one of these is better than the other, but again, whichever pump company you're on, and I know PCM has its own recommendations, and if I try and remember what they are, I'm going to get it wrong, so I'm not going to say. But I can look that up if you want to contact me offline, or contact Reza or whoever your local supplier is. We can get our company recommendations. Another company might have a different recommendation, but it goes along with the elastomer. So again, if you've got a tight fit and a hard elastomer, that's probably a bad thing. But either way, if I go with a tight fit and a loose elastomer, or a soft elastomer, or a loose fit with a tighter elastomer, I don't know. Different companies have different opinions on which one is better. So I can't answer the question directly, but I will say that it will depend on what elastomer you're using. So there's definitely a relationship there. Impact of centralizers above and below the stator to reduce vibrations. What's the preferred distance between the centralizers and the stator? Well, there's preferred, what we always say is never put it very close to the stator. Simple reason for that is if you're using something that's holding the rod in the center, but the rotor has to move eccentrically at the top of the stator. So you have to have some room there. If I make up a number as to what the minimum is, I'm sure someone's going to dispute it, but I would say at least 10 feet. If someone comes in and says, well, I'll run it at 6 feet, well, okay, sure. You've got something there. When you stick it 1 or 2 feet or right at the rotor head, that's bad. Whether it's 6 or 10 or 25 feet, yes, it can certainly be helpful to put one rod length, whether it's a 10-foot rod or a 25-foot rod. One length above the pump is a good thing, and maybe on the second rod above it as well. So you have 2 of them. That can be very helpful for reducing vibrations. But just, yes, never very close to the pump. And again, people will debate, is it 6 feet, is it 10 feet? Doesn't really matter, just make sure it's not 1 or 2 feet. You want to have some room there so the rotor can move. Unless I've missed something, that looks like all the questions. So let's maybe, Benjamin, put the email address back up there, and
there is one more question.
Oh, there is?
Yeah, just published.
Okay. If a PCP is set below the perforations, what can cause tubing and casing communication considering tubing integrity is intact? If you're having communication between your tubing and casing, I'm going to suggest that your tubing integrity is not intact. Off the top of my head, I can't think of an answer to that. If you're seeing flow between the tubing and casing, there's a hole somewhere. Whether that's due to wear, or is it your tubing drain has a hole in it, or has burst prematurely. I've seen cases where just wear has caused the tubing drains to just have a small hole in them. They're not blown, but there's a small hole, same as wear in the tubing. But yeah, if you're getting communication between your tubing and casing, I can't see another answer. I mean, if your pump is really loose, that's if and the pump's not running, and in your pressure test, you'll see some communication there. But yeah, I guess maybe email me offline with some more information, and I can try and help you with that, because communication between tubing and casing suggests there's a hole somewhere. But again, with some more information, I might be able to come up with some other ideas, but that's all I've got on that one for now. Oh, there's another new question there, Benjamin. Oh, someone hasn't finished writing it. Oh, okay, new completion right after workover. Yeah, okay, we'll have to talk offline, because yeah, that does seem strange to me. I'm not sure if you're just pressure testing without the pump running, then a loose pump could be an explanation. Other than that, there's a hole somewhere. That it can happen when, especially, I don't know if you're from Australia where it's water, or if you're somewhere where there's oil. But when you pull tubing out of an oily well, a small hole might easily be missed. They might not see that when they're pulling tubing. So it's possible that there was a hole in the tubing and nobody noticed it, or there's something wrong somewhere. Again, I don't have a better explanation for that, but we can talk offline if you want to send me an email, and we can arrange a discussion. Okay. All right. Well, I think we'll put my email address back up there so anyone can see it if they didn't write that down before. As usual, we will post a recording of this session, but also a recording that'll include the question and answers from tomorrow's session for the Western Hemisphere as well. So we'll combine one of the presentations with both sets of questions, and we'll post that on our website, on LinkedIn. It'll actually go to YouTube, I'm sure. So we'll post the links to that. Give us some time. I know last time I said it would be within a couple of days, and it took maybe 10 days before we actually got around to it. So give us some time. Within the next couple of weeks, I hope we'll see it up there. So anyone who wasn't able to attend today, you can pass that on to them, and they can watch that. We got some more questions. All right, I can try and answer these questions real quick here. Do we have any indication of dry run from PC parameters like torque and current? My feeling on torque is I'm going to say no. Is it possible? Maybe under some circumstances, yes. But I find torque data is it's not sensitive enough to give you that information. I've seen some examples of people who had downhole gauges so they could measure what was happening and measure at torque as well, and you can just see that the sensitivity is not there. The noise in the data is bigger than the slope of the line in most cases, unless you've got a really big pump. So you're not going to control pump off with torque very easily. And I know there's companies out there that sell systems for it. If you were running with downhole gauges and calibrating that against your torque sensors or current measurement from your motors, then if your downhole gauges fail, you might be okay to use that for a while if you give yourself a big safety factor. But by itself, I don't have confidence in torque. Now, if the torque starts to spike or something like that, if it starts to go really higher than what you've seen, then obviously there's something wrong. Whether that's the pump's swelling up badly because it was running dry or whatever. Obviously, a big spike in torque would be a problem. But yeah, other than downhole gauges and fluid shots or something like that to get, and I know fluid shots don't work every case. There's a lot of applications where they don't work. And I know in Australia, a lot of these cavitated wells that they have there, fluid shots don't work. But downhole gauges or anything like that, yes, you can get some good ideas off of that. But yeah, I'm not a big fan of torque. And when you say current, torque is always measured. Well, I should say almost always measured from current. So that's really what you're measuring is current and inferring the torque from that. So yeah, get dry run from that can be difficult. I'm not going to say it's impossible, but it's difficult. So yeah. So that goes on. I guess there's the second part of the question there. So some of the wells with no downhole gauge or possibility to measure flowing bottom hole pressure. I mean, if torque is all you've got, all you're looking for is what was my normal trend and did something change? If something changed, what was it that changed? Is it running dry or is there something else going on? All you know is there's something different. There's too many things that can affect torque. So I'm not a fan of torque measurements, but if you're measuring that and watching it, you can look for changes and then try to explain what those changes are based on whatever other data you've got, flow rate measurements, etc. And then I see there was one more question there. What might cause the rotor to break? The common causes of broken rotors are landed in a deviated section, too much dogleg where the pump's landed. or running on the tag bar. If you don't have your space out right and the pump's on the tag bar, that can cause broken rotors. Those are the two most common, I think. Obviously corrosion and things like that, but once you pull the system to surface, that'll be obvious that that's happened. In rare cases, there could be a weld problem or something like that. And if it's the stator that was welded badly, then it can still cause the rotor to break. So if you see that a break in the rotor is lined up near where there's a weld in the stator, that would be something to have a look at as well. But that's rare. I mean, that type of problem is, the manufacturers all have methods to make sure things are aligned properly, so that shouldn't happen. So yeah, I'm going to say running on the tag bar and landed in a deviated section are the big problems there. First question, how do you manage rotor sizing to match target efficiency downhole? At PCM, we have our own set of rules. We have 14 different rotor sizes for every pump model that we have. And we have an internal document here that lists through a procedure that considers temperature, pump model, elastomer, and effects of viscosity and swell, and can use that as a starting point to help determine which of our rotors is best for your application. Other companies have different procedures, but once you get into a field and start getting experience in that field, you're going to use your experience in that field as a feedback loop to improve your rotor sizing next time. So the guidelines are great going into I shouldn't say great, they're good going into a new field. But what you want to do is look at that and say, was that rotor too tight? Was it too loose? Based on the first few weeks or months of operation, and then adjust that next time. Use a looser or tighter rotor as appropriate. So all companies will do that. They'll have some idea of where to start based on their experience in similar applications. But then once you're in the field, you're going to look at what was the bench test efficiency? What's the actual performance downhole? What's the run life? Do we need to make this pump looser or tighter next time? So it's an iterative process. But we do have a starting point, and like I said, at PCM we've got a document that's very clear on how to get a starting point for any application. Other companies may be more ballpark guesses, they may have something just as detailed as we do, I don't know. But everyone will have a starting point somehow, and then you iterate on that based on your experience. Next question, besides low efficiency with gas production, can gas production damage the elastomer? That's a good question. I think the biggest problem with gas is the low efficiency. When you start getting below 50% efficiency with a standard pump, the PCM HR PCP or slugger can go much higher because it's able to have a linear pressure profile through the pump, so it puts less stress on that rubber. But the important thing, whatever kind of pump it is, there needs to be enough liquid going through the pump to cool, to remove whatever heat's being generated. So that's key. You have to have some liquid going through there, and that depends on what's the temperature. Is it oil or water? What's the friction torque, etc. So there isn't a simple answer to that. We have that rule of thumb that says 50% for, and I've heard numbers as low as 30%, depending who you're talking about. Gas going through the pump for a standard pump, and we go higher for the slugger. But can other gas production damage the elastomer? In theory, yes. You get problems with explosive decompression. Usually that's the CO2 that's doing that, but it's possible that methane can do it. But over continuous long-term performance, that's not so much the problem. It's during shutdowns or when you pull the pump to surface where you start to see explosive decompression causing problems. During normal operation, I haven't heard of natural gas or components in natural gas other than H2S damaging the elastomer. During, like I said, during a shutdown or pulling it to surface, you get explosive decompression. H2S is the one exception to that. H2S will damage the elastomer, absolutely. So if you have H2S in your wells, you need to make sure you're selecting an appropriate elastomer for that. And if it's really high H2S, you might even have problems with that. There are, some elastomers are better with H2S than others, but if it's very high concentrations, you're probably gonna have some troubles there, unless you go to like a fluorocarbon or something like that that can handle higher percentages of that. So I hope that answers that question. In the liquids, obviously, there's things like aromatics that cause problems with the elastomers as well. But in terms of the gas production, we've got, it's the temperature, it's number one, CO2 for explosive decompression, and then H2S is the one thing that will damage your elastomer if it's not selected properly. Okay, question here, it says, we've installed a PCP without a torque anchor in wells with high CO2 because the wedges affect the integrity of the casing during moving tubing string. I don't think there's a question there, but yes, it's just another reason why someone might want to run without a torque anchor. Just the wedges or slips or whatever you want to call them on the torque anchor can dig a little bit into the casing, put a crevice there, and then that's somewhere for a corrosion attack to start. So in a very corrosive application, I can very much understand that someone might not want to use a torque anchor as well. Someone asked if we're going to share the slides. So yes, again, give us a couple weeks to get that up on the website. We will have that up when we can, and like I said, hopefully I know for the last webinar I said it would be a couple of days, and then it took I think about 10 days before we actually got it up there. So this time I'm going to say within 2 weeks we'll have it up. Torque anchorless completion. Can we tack weld the pump and pup joint? Absolutely, you can tack weld that. Depending on the length of your system, because you probably don't want to be tack welding on the rig. So if you're using a really long pump, it might be difficult to be able to do that. But if for anything that's not a maximum length pump, you can do that. But it's the whole tubing string that's affected by torque. It's not just those connections. So where tack welding is useful, there's applications where you might need to put the torque anchor above the pump for some reason. I know there's a few different things you might do that for. So if you do have some special completion where the torque anchor has to go above the pump, then yes, you're tack welding the components below is a good idea. Or you can use something like Baker lock as well. That can work to be able to satisfy those problems. But if that's your solution for the whole tubing string, that gets pretty difficult to do the whole tubing string like that. And then when you have to pull it, you're going to have problems. So where that's a solution really is again, if your torque anchor has to go above the pump, or perhaps if you're using premium tubing through your whole tubing string, but the pump is sold with an EUE connection, then you can put on the pup joint, tack weld it in place, and then put a crossover to the premium connection above the pup joint, and you'll probably tack weld that connection onto the pup joint, but then everything above that's the premium connections with the higher torque rating. So yes. For deviated wells, people think a torque anchor is not needed. Perhaps it's less required in a deviated well because there's a lot more friction there. But that's not a myth or belief that I've heard before. You can try it. If you're trying it and you're not having tubing failures, then it works. That's in my opinion, is if you don't have a reason not to use a torque anchor, you should use a torque anchor. So again, those completions where you've got the second tubing string or instrumentation lines or anything else like that, then yeah, you're gonna have to try something else, and making the torque up higher is good. Maybe in a deviated well, it's less likely to come unscrewed. I don't know the answer to that for sure. But again, my recommendation would still be, if you don't have a reason not to use one, then it's a good idea to use them. And if for any reason you can't use one or don't want to, then again, the higher the makeup torque, the better for the tubing. So avoid that. Somebody asked if we can propose more myths and truths for the next one. The next webinar we do will probably not be a myths and truths webinar, but I did get a couple suggestions after the session we did yesterday for the Eastern Hemisphere of some more myths and truths. So absolutely, if you've got some you want us to cover later, if we collect enough of them, we'll do another one. Sure. So yeah, go ahead and send those. Or any other topic you want to see for a webinar. I mean, these myths and truths, we're giving about 1 or 2 minutes per topic on each of them. But if there's a topic you'd like to see a full 20-minute, half an hour discussion on, please let us know and we can look at that. But yes, so go ahead and send selections. If you're sending us Myths and truths. Again, it probably won't be the next webinar, but maybe in a few months, if we collect a few more, we'll do another one. Can you pump the fluid downhole and watch for backspin to see if it's landed in the pump? Absolutely. If you know the rig crew's got the rotor landed in or they think it's in the stator, but they didn't see it rotating, so they're not 100% sure. Putting a little pressure on the tubing with some water there. If it starts to spin, then you know you're in the pump. You know the rotor's in the stator. So I don't see any problem with that. I know, like I said, people will use a little bit of pressure to help land the rotor in the stator sometimes in those deviated wells. So yeah, just a little bit more, and if it starts spinning, and you know for sure where you are. So I don't have a problem with that. You know, obviously, be careful with safety concerns. You're pressuring the tubing. Make sure that's done safely, and make sure that nobody's got their hand on the rods or anything like that. If it's still hanging in the rig, make sure the swivel's properly greased and is free to rotate, etc. And as soon as it does start spinning, then take the pressure off. Just be safe. Someone makes a comment here. Fluid is an important consideration because swelling may affect the elastomer, and you will gain efficiency, as Paul mentioned, is better based on field experience. So yes, if you're going into a new field, getting a swell test done send your fluids off to whatever pump companies you're looking at buying a pump from, and let them do a swell test with their elastomers, and then you can come back with recommendations for which of their elastomers is better. I'd always be cautious comparing swell tests done by one company to the swell test done by another company, because if they're not doing it the same way with the same size of coupon, etc., you can get different results. But within that company, at PCM, of course, we're going to test all ours the same way with the same size, so we know which of our elastomers will be better for your application, and the competitor will know which of their elastomers is better for the application. But if you want to actually compare PCM to a competitor, then I would recommend getting the elastomer samples and going off to an independent third-party company. And there are companies out there that do swell tests, and they're fairly cheap, I think. So let the third party do them, and make sure that the coupon size is the same if you want to, because if they're different, if someone's got a 3 millimeter thick specimen, someone's got a 5 millimeter, and someone's got a 10 millimeter, they're going to swell differently. The thinner the specimen, the higher that initial swell will be. The total swell should be the same if you can leave it long enough, but if you're only doing a test for a week or so, a thicker specimen might not be fully swollen yet, and you can't tell that from a simple before and after measurement if it's fully swollen. So again, making sure you're doing them the same. Can gas cause problems with the elastomer bond to the housing? There's a very good question. I've heard that theory. As far as I know, it hasn't been proven, but there are people out there who believe that yes, it can. I don't have any reason to argue one way or the other. So I'm not going to say yes or no to that, but I'm going to say it's absolutely a possibility that it can. I think most people are concerned about water, and especially at high temperature, causing failures to the bond, but I know there are people out there worried about gas doing it as well. So that doesn't answer your question, unfortunately, but if you're concerned that it's one possibility, then absolutely. And because it's a PCM webinar, I'll just mention that at PCM we have the X-bond solution for problems where there's bonding problems. It's a mechanical lock system that greatly improves the bond. So just mention that. If you're interested in that technology, certainly let us know and we can talk more about it. But the simple answer to your question there is it's possible, but I don't know for sure. Are there any more questions? Maybe I'll put my email address back up there for now. I'll just watch to see if any more questions come in. In the meantime, if you didn't write my email address down before, or you don't have it, then there it is. But now I'll just start a conclusion here until another one shows up. Did another one just come? No, I don't see it there. All right, well, again, I want to thank you all very much for your time in attending today. It's always a pleasure to talk to customers or competitors or anyone else who might happen to be listening. and I always like to hear the questions and see the different things you've experienced as well. So again, I greatly appreciate your time in attending today, and the slides and presentation will be available hopefully soon, but certainly within a couple of weeks.
Well, thank you very much. So as Paul said, we'll be posting this presentation and recording at some point soon. So keep an eye out on our website and LinkedIn page for more information. Paul, thank you very much for your time. For all those that are still there and listening to us, we really appreciate you taking the time, and hopefully you found it useful. If there's anything you're not sure about, please do reach out to us or any of the PCM team members or Paul direct, and we can have one of our engineers take a look at it and hopefully come back to you with an answer. We'd also love to have some feedback about our sessions. So anything you think we can improve on, do let us know. Or if there are any particular topics or suggestions that you'd like us to raise in future sessions, again, do let us know. We'd be more than happy to consider them when we're planning on holding future events. At this stage, we look forward to seeing you again soon, and thank you very much.